Now I'm recording this lecture because I'm getting a lot of messages that please give us the flow, give us this live session videos. No, the live session recorded videos will not be provided at any cost. That has been communicated multiple times, so there is no point following on the same. So please look into this revision video for the time series analysis. Okay, so this is the flow chart. I'm creating a duplicate page as well. So you design the trend model. What are the two different trend models we have? We have the trend model, which is like this, which is the linear trend model, and this, which is the exponential trend model, but the name given to the trend model is the log linear trend model. Can I use the trend model? First of all, we have to check, is it a white noise process or not? What is the meaning of white noise process? There are three words which are important for white noise process. In the assumption that the error term is normally distributed with a mean of 0 and a constant variance, white noise only stand for three words: whether the error term is independent, error is independent. When I say the word independent, it means that the correlation with anything on this planet is 0. The second thing is the mean of the error term. The mean of the error term is 0. And the third is the variance of the error term is constant. If the three properties are satisfied, we say that okay, it follows the white noise process. Now, can I use the trend model? First of all, I'll check what. Is it a white noise process? Yes, it is a white noise process. Awesome, use the trend model, whether it is a linear trend model or whether it is a log linear trend model. Now, what if it is not a trend, as in the trend model does not follow the white noise process? If the trend model does not follow the white noise process, you have to check for covariance stationary. Covariance is stationary in what? Error term or y? Y. Do not do this mistake. You are not going to check for covariance stationary property in the error term. You will check the y you are trying to forecast. Whether that y follow the covariance stationary or not. Okay. First, let's talk about what is the flow. Check for the covariance stationary. No, it's not covariance stationary. Then let's forget this section because that section is not correct. No, it's not covariance stationary. You cannot use any model. Simply, if it is not covariance stationary, that is the final result after all the testing, you cannot use the model. But okay, if it is covariance stationary, you can use AR model, MA model, and ARMA model. Autoregressive model, moving average model, and ARMA model. Now, what is covariance stationary? When I say covariance stationary, then it is stating that y is having such a structure which we are trying to explain with the help of plotting. So the red graph that I would be plotting, the red graph is your y, which is covariance stationary. And this white line is actually the long-term y mean. This is actually the long-term y mean. Now, is the mean stable and finite? Yes, the mean is stable and finite. Because if I would have plotted something like this is the long-term mean, and this is my y, then the y mean is changing with time. So your mean is not constant in this plotting. Here the mean is finite and constant. So the first property of the covariance stationary, the mean is finite and constant. The second property of covariance stationary is that the variance is constant or stable or finite. Okay. So if you look into this height, the distance from the mean is stable, it's constant, it is finite. However, if I plot something like this, you can see that the variance is changing. It's not homoscedastic, it is heteroscedastic. So variance has to be stable and finite. It should be constant. Okay, the third is the covariance structure should be stable and constant. So if I try to break the section into different lag, so assume the correlation between this section and this section is 0.6, then the correlation between this section, the second section and the third section will also be 0.6, and the correlation between the third section and the fourth section would be also 0.6. As in, the covariance structure is constant. What does it mean? It means that if yt and yt minus 1 has a correlation of 0.6, then yt minus 1 and yt minus 2 will have a correlation of 0.6, and so and so forth. Yt minus 2 and yt minus 3 will have a correlation of 0.6, right? However, if yt and yt minus 2 has a correlation of 0.4, then yt minus 1 and yt minus 3, now there is a lag of 2. Earlier there is a lag of 1. Now if there is a lag of 2, then the correlation would be constant. So that is the meaning of the third property in the covariance stationary property of y. When I say the y is covariance stationary, it means the mean is stable and finite, the variance is stable and finite, and the third is the covariance structure is stable and finite. So you will check whether y is covariance stationary or not. If it is yes, then you will design AR model, MA model, and ARMA model. Now, even in the AR model, MA model, and ARMA model, so what is AR model? AR model is stating that yt is dependent upon yt minus 1 or yt minus 2 or yt minus 3. Y is dependent upon the previous value. So when yt or y is dependent upon its previous value, we call it as autoregressive model, and it could be yt minus 2 or yt minus 3 or yt minus 4. Okay. MA model, when yt is dependent upon the previous error term in forecasting, that is called as moving average model. Okay. An ARMA model is when yt is dependent upon both the previous value, it could be yt minus 1, yt minus 2, yt minus 3, or the previous forecasting, it could be et minus 1, et minus 2, et minus 3. Okay, so you design AR model or ARMA model or MA model. So again you will check for what? White noise process, where in y or error term, so you design the model y is equal to b naught plus b1 into yt minus 1 plus b2 into yt minus 2 plus error term. Now this error term is a Gaussian white noise process. This error term should be Gaussian white noise process. What is the meaning of Gaussian and white noise? White noise stands for the same stuff that we have discussed earlier. The error term is independently distributed with a mean of 0 and a constant variance. But if I say the error term is normally independent distributed with a mean of 0 and a constant variance, that becomes a Gaussian white noise process. If it is a Gaussian white noise process, error term is also normally distributed with a mean of 0, independently normally distributed, where the correlation of error term with anything in the planet is 0, the error term mean is 0, and the variance of error term is constant, I will call it as a Gaussian white noise process. If it is a Gaussian white noise process, awesome. If the AR-MA ARMA model error term is following a white noise process, awesome, you can use the AR model, ARMA model, or MA model. But if it is not, pathetic, you can't use any model. Now, even after designing AR model, ARMA model, or MA model, then you have to check for unit root, the problem of unit root, and the test that you need to know through which you will test whether there is a problem of unit root, which is also called as, the other name of unit root is what? Random walk. They are related. You will check for unit root with the help of decay Fuller test. What test? Decay Fuller test. And if there is a problem of unit root, then yes, your mean is what? Infinite, because If you remember, we discussed y mean of AR model. Y mean of AR model is b0 upon 1 minus b1. Right? If this b1 is 1, then there is a problem of unit root and your mean will become what? Infinite. If that is the case, then you will resolve with the help of first differencing. In the first differencing, you will try to predict the change in yt due to the change in yt minus 1, the change to change. That is called as first differencing. And if the problem of unit root get resolved with the help of first differencing, then yes, you can use the AR model, MA model or ARMA model. However, if there is no problem of unit root when you are designing AR, MA, ARMA model and there is no problem of Gaussian, that it doesn't have the Gaussian white noise process, then awesome, you can use AR, MA, ARMA model. Okay, apart from that, we also discussed about a very important point, that is ACF and PACF. Okay, when I write a equation yt and yt minus 1, equation with yt and yt minus 1, then the correlation is equal to what? The coefficient. When I am trying to write the equation between yt and yt minus 1, then the correlation is r square and the coefficient would be what? B square. This is called as Joule-Volcker equation or whatever you say. And similarly, if you keep on increasing, it is yt minus 2 and yt minus 3, then the correlation would be r cube. So basically, the correlation between h lag would be correlation raised to the power h. That is ACF. But the problem with ACF is that ACF is a dirty correlation between yt and yt minus 1. However, there is no dirty correlation between yt and yt minus 1. But dirty correlation between yt and yt minus 2, dirty correlation between yt minus 3, and dirty correlation where the lag is more than 1. Why? Because assume that I am trying to find out the correlation between yt and yt minus 3. Now, I said, okay, the correlation between yt and yt minus 3 is 0.4. But if you look carefully, yt minus 3 is first impacting yt minus 2. Yt minus 2 is then impacting yt minus 1, and then yt minus 1 is impacting yt. So actually, when I'm trying to find out the correlation between yt and yt minus 3, I also have the correlation impact due to yt minus 2 and due to yt minus 1. So I want to remove that correlation impact and really want to find the pure autocorrelation or pure correlation between yt and yt minus 3. And ACF is not sufficient to provide it, because ACF will give you that dirty correlation between yt and yt minus 3, where there would be component of correlation of yt minus 2, the dirtiness of yt minus 2 impacting yt minus 1, and then yt minus 1 impacting yt, or yt minus 1 is impacting yt minus 2 and yt minus 3, so and so forth. For that, we go for PACF. So in PACF, if I write an equation, if I do a regression, that yt is equal to beta naught plus b1 into yt minus 1 plus b2 into yt minus 2 plus b3 into yt minus 3, then these coefficient will give you the pure correlation between yt and yt minus 1, yt and yt minus 2, and yt and yt minus 3. So b1, b2 and b3 are the pure autocorrelation function, or you can say partial autocorrelation function. Okay, we discussed that. We also discussed something which is related to lag operator. Now if I write L into yt, it becomes yt minus 1. If I write L square into yt, that becomes yt minus 2, so and so forth. Right. Now with the help of lag operator, we also entered into the discussion of Wirth's theorem. And we also discussed something called as invertibility. If Y's covariance is stationary, then they say that AR1 model is nothing but MA infinite model. And MA1 model is nothing but AR1 model. That is quite interesting, but we can prove this with the help of lag operator. Now, What is AR model? So AR model can be written as yt is equal to b naught plus b1 t plus error term et. For the time being, for the simplicity, just remove b naught. Okay. So I can write it as, oh sorry, this is not the correct equation. I have written t. That is a trend model. So I will write y is equal to b naught plus b1 into yt minus 1 plus error term. And for simplicity, I will remove b naught. Now I would write y minus, sorry, I will take this in this side. I will write y minus b1 yt minus 1 is equal to error term. I would convert it with the help of lag operator. b1 into L into yt is equal to error term. So I take yt common, that is 1 minus b1 into L is equal to error term. Yt is equal to et upon 1 minus b1 upon L. If you look this carefully, this is very equal to the summation of a GP series A plus AR square till infinity. So I can write it as the summation is A upon 1 minus R. So basically 1 upon 1 minus BL is just the summation of a GP series where A is 1 and this BL is your the R through which you are increasing your GP series, the coefficient with which you are increasing the GP series. So I can write it as ET into, the first term is 1 here, so I will just write 1 plus B1 into L plus B1 square into L square plus B1 cube into L cube till infinity. Okay, so I converted into this. So YT is equal to ET. So I will multiply ET with 1, then ET with B1 into L. So when I multiply ET with B1 into L, so if I multiply L into ET, it will become what? ET minus 1. So I will write it as ET minus 1 into B1 plus B1 square into ET minus 2 because it is L square, B1 cube into ET minus 3 plus till infinite. So you can see that we started from what? We started from a AR1 model and we reached to MA infinite model. Similarly, if you start from, say you write a equation yt is equal to minus b1 into et minus 1 plus et. If you start from here, this is a MA1 model, and if you use the right L operator, that is the lag operator, you will prove that this equation is nothing but a equation where this can be transformed into an infinite AR series. So that is the property of invertibility. Okay.